Okay, welcome back everyone. In this video we're going to be talking about the impulse momentum theorem, and we're going to build off of what you learned in the previous video about how we can write momentum using Newton's second law. So what you learned from that video is that you can really write a force as a change in momentum occurring over some change in time. And if we multiply each side of this equation by delta t, what we get is F times delta t is equal to delta p. So a force times a time interval causes a change in momentum. And this makes sense if you think about it. If you want to change an object's momentum, you have to apply force over a particular amount of time. Now we can take this one step further, and we can write on the right side that a change in momentum is actually a change in mass times velocity. And well, most of the time we don't really think about mass changing, so at least for right now we can write this as F delta t equals m delta v. So basically what this says on one side is that if you apply a force for a certain amount of time, that it will cause a mass to change its velocity. And this is what we call the impulse momentum theorem. And this is one of the big important equations of this unit. So important that I'm actually going to highlight it. Okay, so there you go, the impulse momentum theorem. Now let's look carefully at what each side of the equation is. The left side is what we call the impulse, and it has units of newtons times seconds. And going back to our whole idea that from F equals ma, the left side are the causes, you could think of impulses as causes of changes in motion. The right side is the change in momentum, and this has units, it appears, of kilograms times meters per second. But as it turns out, a newton is actually 1 kilogram times 1 meter per second squared. So when you take that and multiply it by seconds to get newtons times seconds, you actually end up with kilograms times meters per second. So if you remember previously, I said that the units of momentum looked awfully close to force. Well, here's why. If you take the units of momentum and divide by seconds, you're going to get force. Okay, so on the left side are causes, and on the right side are effects. Okay, so as an example, let's look at number 39 on page 209. So in this problem, it says a volleyball is traveling toward you. For part A, the question is, which action will require a greater force on the volleyball? You're catching the ball or you're hitting the ball back, and why? And so it turns out, okay, so here you are. Here's the volleyball coming towards you with some speed. If you think about it, what would cause a greater change in momentum? Stopping the volleyball or actually making it go back in the opposite direction? Well, it turns out that making it go back the opposite direction effectively is twice as much force, because not only are you stopping it, you also have to push it back to go the other way. Okay, so reversing the direction. Because basically the change in velocity is twice as much as simply catching it. And you know this if you've played a sport, that if you try to reverse the direction of something instead of merely catching it, it's a lot more force. Okay, think about, for example, catching a football as opposed to punching it back in the other direction. Okay, now for part B, we actually want to calculate the average force if we have a situation where this is a 0.45 kilogram volleyball and it's traveling toward you with a velocity of 4 meters per second, so that's v initial, and then after it leaves your hand, it's going with the final velocity of 7 meters per second. Now, one thing we have to be careful about is the directions here, and we'll say that to the right is positive. So what that does is it actually makes the initial velocity negative and the final velocity positive. This is a pretty big error that people will make, is not getting those signs correct. Okay, and we're told that the contact time is 0.040 seconds, and we want to know the average force. Now, the reason we call it an average force is that in reality, if I looked at the force versus the time, there'd be some sort of a bell curve. You know, the force doesn't happen for just a fraction of a second, but that's not a really important detail. So we apply the impulse momentum theorem. F delta t is equal to m delta v, and we remember that delta v is actually v final minus v initial. So F is what we want, time is 0.040 seconds, mass is 0.45 kilograms, and now here's the tricky part. V final is plus 7 meters per second, and we must subtract a negative 4.0 meters per second for V initial. That's a crucial thing here. Do not forget about that. So that actually turns into adding, and so the force is basically 0.45 times 11 divided by 0.040, and that comes out to approximately 120 newtons in the positive direction. So that would be our final answer. So again, one of the key concepts for impulse momentum is that when we change the momentum of an object, m delta v, we have a choice as to whether or not we have a large time interval or a large amount of force. And there's reasons why each one might be preferable. Okay, so there you have it.